Okay, great. So I'm Quentin Kaiser. I'm a lead security researcher at OneKey. It's a company that does automated firmware security analysis. And today I'll speak about the year-long journey that took us to the open sourcing of Unblob, which is a firmware extraction tool. And we'll see all the details. So to get a shared understanding of why we developed Unblob, this is what we do. People can upload firmwares, we do automated extraction, then we perform firmware composition analysis. Based on that, we do security checks that allows us to provide compliance and reporting to customer, but I'm not here for a marketing talk, so let's focus on the subject at end, which is upload and extraction. So I joined the company 18 months ago, and there were a few issues. So on the upload side, we are receiving lots and lots and lots of different firmwares from different sources, part from our internal scrapers that download firmwares from vendors and manufacturers. We get uploads from our customers, but also from students or from researchers at universities, which leads to different issues on their own, like high amount of uploads, lots of concurrency. We love our customers, but we should not trust them, especially since we don't know the source of those uploads or where they found the actual firmwares. On the extraction side, they were using binwalk initially, which led to a lot of timeouts. There is a very limited format support, and of course the memory footprint was quite intense on large firmwares. So in conclusion, we need to automatically extract firmwares of arbitrary format coming from untrusted sources and do this at scale. So that's why we started working on Unblob, which is a firmware extraction framework. It can parse unknown files and match on more than 30 different formats, specifically archives, compression streams, and file systems. Internally, we support like 70 formats, like we have our internal handlers. But at the moment, the open source version, you have like 10 archive formats, 10 compression streams, and 10 file systems. When we started developing Unblob, we had 4 clear objectives in mind that are derived from the problems I just mentioned. So we wanted to be accurate, we wanted to be secure, extensible, and fast. So let's first look at accuracy, and we'll see why other existing extractors are problematic. So you get a big binary blob, and Unblob will start scanning the files up until the point where it will find a signature. Like most of the formats, be it compression, archive, or file system, they will start with the same magic bytes that you can match on. And the magic thing with Unblob is that specific handler, format handler, will receive reference to the file and the start offset, and by following the standards, so parsing the header or trying to decompress up until it reaches an error, we will calculate the exact end offset of that chunk of data. So in this case, it's an LTMA compressed stream. We carve it out to disk, we decompress it, and then the decompressed stream is then fed back to Unblob recursively. The scanning continues. We identify something else. Again, we can calculate the end offset. So the end offset we calculated for some formats, the whole chunk size is located in the header. Sometimes we need to just parse the different subheaders. Well, there's lots of parsing in there, but anyway, we have specific end offset. We carved it out. It's an XFS file system. We extract it. All the files within the XFS extraction directory are then fed back to Unblob recursively. So it's a big change compared to other extractors in that previously or other scripts and techniques, they will match this beginning, and then they will feed to the decompressor or the extractor everything from the start offset up to the very end of the file. If you're trying to decompress a stream and you have like garbage data at the end, it will fail and the decompressed data won't be there, or your extractor will crash silently and you will know nothing about this. Another thing is that since we can identify specifically the start offset and end offset of those chunks, once the file has been fully scanned, we can identify turn the unknown unknowns into known unknowns. So we can carve them out to disk. And usually when you look at this, these unknown chunks on disk, this will be null padding, 0xFF padding, or custom header. And this allows us to identify vendor formats that we should add support for in Unblob. So, speaking of accuracy, it's really difficult because you would think just following the standard will be sufficient to support formats, but it's not. I'll give you two examples. We have many more, but for most of them, I can't discuss them publicly. So I'll start with SquashFS. So SquashFS version 2 gets released in the early 2000s with two signatures. One for the little Indian version, one for the big Indian version. So SQSH for squash and HSQS, which is byte swapped. So version 3 comes along, and then version 4, and we already have a problem there because per the standard, there should only be version 4, big Indian. Little Indian is non-standard, but some vendors chose to implement it anyway. Then DDWRT chose to use TQSH as their signature for no specific reason. Broadcom did it, some unknown vendor yet to identify also changed the signature. And then AVM chose to, well, let's put the header in big Indian and the chunks in little Indian, because why not? And then this is quite recent. I'm still working into this one. So Netgear used the exact same signature. So this one, but they don't follow the standard. They're using this LZMA plus XZ compression, which of course, like doing 2 paths of compressions is always useful. So this is the standard, and this is not standard. But if you want to extract any kind of firmwares, you need to support all of those. Let's switch to this one. So this was making Unblob fail on some CRAM-FS. So this is the expected CRC, and this is the observed CRC. This is weird. Something's off. So at Cisco, they decided that, well, it's still unclear if either it's an implementation mistake or they don't mind following the standard. So it's a CRAM-FS, but in Cisco world, the CRC is byte swapped. So we had to add support to Unblob, and working on Unblob is a constant stream of those vendors not following standards. So the second objective of Unblob is security and, well, to be secure. And we are looking at 4 main avenues. Extraction attacks. So extracting untrusted firmwares is kind of like pretty much detonating malware. So you should be very wary of all of potential path traversal and extraction attacks, or zip bombs, for example. For stability, so we run Unblob in production, so it needs to be stable. We don't want to get any crashes. There is the question of privilege. I'll get back to this, and of course, dependencies. So for extraction attacks, we audited the third-party extractors that we rely on, and we found path traversal vulnerabilities in Jefferson, which is the JFFS2 file system extractor, in UBI Reader, which is the UBIFS extractor, in YAFShiv, the YAFS file system extractor, and in binwalk, specifically in the PFS file system extractor. And also a few other logic bugs related to inode handling. Hi, Stefan. But I'll just show you a few examples. So this is Jefferson. They were not even trying to protect against path traversal. So if you were to craft a JFS2 file system with ... in a name, it would be written outside of your extraction directory. Similar thing with UBIFS. So easy to identify, easy to patch. This one's a bit different. It's in YAFShiv. So we see that they were trying to protect against path traversal. But this is totally, this is insufficient because you could craft a YAFS file system where the name starts with /. So /etc/ something, and it will be written there. So this is not sufficient. And the last one is, so the story actually started like this. It's on our internal Slack. This is on binwalk. This is the PFS file system extractor. So the bug is there. This line and this line. So basically, the condition will never be true. This will never be, this path will never be taken because os.path.join does not resolve the absolute path. So if you do if you join /temp and ... something, the ... will stay there, and alt file path will always start with .dir, so the condition will never be true. So the fix is super simple. You just resolve the absolute path. So it seems not important. Just looking at it this way, but I'll show you. So I posted this on Twitter a few days ago, I guess 2 weeks ago. So this is a 0-day against Envelope. There is a pull request to fix it. It's still open. The one's looking into it, so I'll just do a demo. All right. So I got this file open. I'll download it. The internet connection is quite slow. Okay. So we see I'm downloading FG whatever. All right, so I'll parse the file with binwalk so you can see what's in there. So we got a JPEG image with a PFS file system embedded in the ICC, which is a color profile. If I do the extraction, no ends. You get rickrolled. It should load YouTube. Hopefully. Connection is quite slow. But anyway, the idea is that by abusing the path traversal, I'm writing a binwalk plugin to the binwalk plugin directory, which is always located at the same location. And interestingly, binwalk constantly tries to load plugins as it is executing for some reason. I don't know why. But in a single run, just trying to extract a file, you will get code execution on the analyst workstation. So this is a very important problem we're trying to protect against with Envelope. In terms of stability, we first tested Unblob, the whole code base. We found and fixed 19 bugs so far, which are mostly logic bugs. We have integration tests with integration test files, and all of our we managed to build a corpus out of those. If you go to the GitHub repo and filter all the issues with the fuzzing label, you will see all the bugs, if that's of interest to you. Regarding dependencies, or dependencies are locked, we are using Poetry, so we are protecting against potential supply chain attacks. And it's even better if you use Nix, but I will get into Nix a bit later. Also, we took the kind of opinionated decision to not require elevated privileges, which means we can't create special files like block devices or character devices. It's okay for use, but for example, if you wanted to emulate a device with this file system using QEMU, for example, this decision may limit you in what you can actually emulate. Third objective is to be extensible, and I'm using the analogy with Metasploit. So when HD Moore started working on Metasploit, it's because he was spending all of his time validating and sanitizing exploit code. And it's pretty much the same situation at the moment if you're doing embedded firmware security and looking at all those vendors' formats. Like, everyone is publishing their own tools. This is like for Netgear, then for Hikvision, for Tretech, Yelling from the guys at Synactive. So everyone is like rewriting the same thing over and over and over again, mostly in Python. And then the tools are published and they're not maintained. So the idea is to provide with Unblob a firmware that will do all the heavy lifting, and will constantly maintain all the potential format handlers that you add to it. Last objective is to be blazing fast. So we took a few decisions there. We are using Hyperscan, which is an Intel pattern matching library, which takes advantage of architecture opcodes, like all of those SIMD operations. We were initially using Yara to do pattern matching, but we found so many bugs and it was getting quite slow the more handler we were adding, that we switched to Hyperscan, and it's the best decision that we took. We are relying on Rust for memory-intensive operation, like calculating the Shannon entropy on unknown chunks. At the beginning of the talk, I showed you like the unknown chunks being carved out to disk. This is interesting to calculate the entropy so that we can detect whether it's heavily compressed or potentially encrypted. And the last thing is that we are using modern Python, using mmap file, which means it's even faster. Just to take a look, I calculated, so I ran Unblob on, I think, 1,000 samples that I picked up randomly from our corpus. Most of our corpus is below the 500 megabytes line. And everything is like way below 2 minutes of extraction time, and you get like kind of a trend if you look at the actual extracted size. All right, so just a quick shout out to the team behind Unblob. It's not only me, it's Alf, a very dedicated Python development team, and my research team. All of them are there, so thanks to all of them. So the objective is to teach you how to get started with Unblob, or you can create handlers, or you can create extractors, and I'll switch to this. So there are different ways you can install Unblob. You can use Docker, you can use Nix, or you can go the hardcore way and use source. So for Docker, we have a container that is published to the GitHub Docker registry. We just recommend that you use the -- pool always, so you always get the latest version. It's under heavy development, so if you don't do this, you won't get the latest fixes. And we are using bind mounts with the -v option so that you can get the input directory to put your firmware file there and the output directory where all the extraction will be located. We also have a Nix nerd in the team. So Nix is a way to perform reproducible builds. And if you do Nix profile install, it will install Unblob with all of its dependencies in a self-contained environment that won't pollute your whole file system. And the last way is just clone the repo, use poetry to install it. So let's extract some stuff and we'll see how it actually works. All right, so I'll start with an OpenWRT image, so you'll see how it actually looks like. So poetry run unblob will run in verbose mode. I'll extract to /them/out, and I want to extract this. All right. So it's quite verbose at the moment. You'll see it's part of future work. So the extraction is done, and we can go into the extraction directory. Just take a look. All right. So all the files are named after their start and end offset in decimal representation. So we see that we have like 64 bytes of unknown data, an LZMA stream, followed by another unknown chunk, and then a squashfsv4 file system, followed again by some unknown data. I'm using the hx command, which is basically an alias for xdump in ASCII. So if we look into this one, it's basically the OpenWRT custom header with the metadata about this package. So whenever we get uploads and that we have like a custom header, it's super easy. Like we take an xdump of this value, we open a ticket, and whenever we have time, we extend like the list of unblob handlers to support those. I'll quickly show you the different unknown chunks. So between the LZMA and the squashfs file system, we get null bytes. So like this is proof that our extractor is actually accurate in identifying the start and end offset of those valid LZMA and squashfs. And if we look at this one, it's just 0xff padding with dead code at the end, which is a marker used by OpenWRT. If we look at the LZMA content, it got decompressed, and within the decompressed LZMA stream, we found other things. I'll just... and this is actually the Linux kernel. So the LZMA stream is actually the BZ image that is used to boot. We have handler that we have yet to open source that match on those kernels, that makes things better than this output. But anyway, you see the point. And of course, the last one is this squashfs file system got extracted. You get your usual suspects there in a Linux repo. One thing we can do with Unblob is also to generate reports. So you can generate JSON reports that will contain a lot of metadata about the extraction process. So I'll just do this now. So -f, so we overwrite, then report. All right, and we can have a quick look at this report structure. So this JSON report will contain permissions information, the magic, MIME type, the hashes in different formats for all of the files that were analyzed, the files that were extracted, the files that were decompressed. The objective for the future is to store even more metadata prior to the extraction. You have some formats, for example, like tar, which store the owner information as text. So, for example, if the tar archive was created by Alice and is extracted by Bob, we want to store the information that it was created by Alice, because once it's extracted by Bob, the information is lost, because the UIDs are different and because the tar format is not relying on this owner information to do anything on disk, actually. One interesting thing you can do with those reports is to generate diagrams and visualizations of what got extracted. So I'll just start my Jupyter notebook. All right, so we're basically using Plotly, reading the JSON report to generate the diagram. Okay, so this one is a tree map view. So you see the overall firmware, then you get the SquashFS on one side, then the Bezier image on the other side, and whatever got extracted from the SquashFS is grouped by file type. But you can also do sunburst visualizations. Like this, and you can navigate just clicking on any inner circle to understand what is actually contained in any lower layers of your firmware. All right. I'll switch to how to write handlers and show you how easy it is to do it. We used to do the live coding demonstration, but in the end we have just tags in our GitHub, in our Git repo, because it's easier. So. I'll quickly show you an example. It's a Netgear firmware for the R7000 router. I'll just extract it. All right. So. What's interesting is that this Netgear firmware format is actually an CHK format, if you look at it. So it always starts with this these magic bytes, like star, dash, dollar, caret. So we want to write a custom handler for this CHK to take it into account. Hope this is visible. Yes. So the idea with envelope is that you just need to create a handler class that should inherit either handler or struct handler. All of those handlers must define a patterns list, which can be defined as strings or X strings. So in this case, those are the 4 magic bytes that starts the CHK header. And all of those handler must implement the calculate chunk function, which takes a file, reference to the file, which is our mmapped file, and the start offset where the pattern was actually identified. With the struct handler, you get the ability to define a structure in C. So this is the actual structure of CHK. So you get the magic, the header len, and then those firmware contains two things. Well, one or two things, a kernel and a rootfs. So you get your header, then the kernel, then the rootfs. So if you know the length of each, you can exactly calculate the end offset, which is or start offset plus the length of the header, plus the length of the kernel, plus the length of the rootfs. And the struct handler just supports it with this parse header function. So if I run the extraction again, this time we see the header, which is printed out in the console. Our calculation is so good that the chunk covers till the end of the file, and we didn't define any extractor yet, so it just stayed there. There are no extracted content. So now we need to actually implement an extractor for CHK. Okay. I'll switch to the rest. Well, I get connectivity for some reason. Anyway. So for extractors, you can implement them in Unblob, but for most of our formats, we rely on third-party extractors, like the ones I named, like Jefferson, Sasquatch, UBI Reader, Yavshiv, but for the most complex one, we just wrote them in Unblob. In terms of future work, we want a clean report of the extraction process in the console. As you've seen, it's quite verbose and there are like struct logs everywhere. So what we want is to provide just a clean summary to end users with, for example, X% of the firmware was properly identified, Y files were extracted. Just to get a nice and clean summary. As I mentioned with the tar archive example, we want to increase metadata extraction. So prior to actually doing the decompression to disk or the extraction to disk, we want to collect any kind of metadata information that can be collected from the header or metadata structures on those formats. One interesting example are uboot uimage, where in the header you get the load address. It's of great interest to us in the firmware analysis pipeline, so we want to keep it in our JSON reports. Unknown chunks auto-identification is also a big project. We've got some proof of concept, but they're not public yet. Basically, an unknown chunk is like the one I've shown at the very beginning that contains like null bytes or 0xFF bytes. They're basically Python objects. We want them to be able to perform introspection, so looking into their own memory and mutate themselves. So if an unknown chunk is full of null bytes, it would mutate into a null padding. So it would be even visible from the file name. The analyst don't even need to like do an xdump of the chunk. It would be just .null padding or .ff padding. It would be even cleaner. Of course, we want to extend the format support, any kind of vendor formats that you can think of. We'd like to support it. you are all very welcome to contribute, test it on your weirdest files, any kind of weird files, just run envelope onto it, report bugs, request support for new formats. We got a few of them since this summer when we presented at DEF CON for QNX IFS and Qt resource file, if I'm not mistaken. Of course, if you used envelope into your own projects, submit a pull request. If you're not a professional Python developer, the team will help you, and there are lots of guardrails into the way we develop. We're using Black to lint the Python files. We are using Vultr to identify dead code. There are lots of integration tests that are running, so it's really difficult to make mistakes writing envelope code. I'll check if... Okay, cool. Step 2. So we want to do the CHK extractor. So an extractor must inherit the extractor class, and this class has a single function that you must overload, which is the extract. 2 parameters, in path, which is the path to the carved out chunk that was written to disk, and the outdir, which is the extraction directory where you need to perform your extraction. So basically this CHK extractor is parsing the header, seeking to the end of the header, and then dumping the kernel chunk and then the rootfs chunk. So if we rerun envelope with this addition, we get something new. All right. So in this case, there is no rootfs in this CHK firmware. We only got the kernel. And if we go to the kernel, we still have a 28 bytes of unknown data. HDR0, it's actually another format from Netgear called TRX, or used by Netgear called TRX. So next step is actually to implement a TRX format handler with envelope. And it will block again, so I'll switch. All right, I'll go back to the code if you have time, but in the meantime, thank you very much for your attention. Incendiary emails can be sent to research@onekey.com. Thank you. Do we have any questions? Yes.
It seems that you're using a lot of different tools to extract, like 7-zip, tar, and whatnot.
Yeah.
Are you sandboxing tools? Are you fuzzing them?
So we audited mostly the Python-based extraction tools, and other, like, in our infrastructure, we are using sandboxing, like, on top of envelope. We're not relying just on the fact that we audited them. We are using FireJail with, like, everything disabled. That's
And also, do you plan to open source your fuzzing infrastructure? I haven't seen the fuzzers in the source code.
Yeah, the fuzzer is not public, but we could make it public. It's basically feeding off so all the integration tests. For example, if I were to, yay. That's it. So if you run PyTest on the repo, you will see that it tries to run all the handlers on different integration test files. So if I do PyTest3, it will collect the samples. But anyway, you can, our fuzzer will just take all the integration test files as corpus and do like mutation on them and just feeding them to envelope to see what's happening.
Thanks.
And do you have what you showed to create a new parser? Is it available on your GitHub repository so that we can actually do another one?
So if you go to unblob.org and go to development, there is a whole guide, like developer guidelines, that explains with really simple example how to write a new handler. So first thing, setting up the dev env, and then like writing handlers. So this is a really super simple example that you can start off to write your own handlers or extractors. It's on unblob.org.
Just another question on these handlers. So they could handle the case that we saw in the morning with the printers where they need to deobfuscate the binary first before then. And then they could pass it in a queue to the actual extraction. Would that also work?
So if we take the Canon printer example, they could write a handler that would match on like the first layer based on the 4-byte header, then perform the deobfuscation there, and then do the extraction for the second layer by writing another handler. So any kind of, it's not only limited to like extraction. If you have a vendor that performs some kind of weak encryption, or if you can derive the key based on the firmware header, or if the key is known, you can also do it but it's also based on like you're making the assumption that you can identify that the binary blob is encrypted using this specific technique. So you need the header to be in plain text. Another way is to specifically mention the handler that you want to run if you precisely know that the blob you are trying to extract is encrypted with this technique. Last question. All right. Yeah.
Thank you. Do you have experiences or plan to support weird and obscure encryption mechanism, compression algorithm that implemented by some vendors, like hypothetically Siemens?
We did for some. I don't have the exact examples in mind, but yeah, we have like 40 internal handlers, and they are for bare metal image, like you can think of Intel X or Motorola X records, some custom compression streams implemented by vendors, weird archives or file systems. For example, ECOS ROMFS, which is not traditional ROMFS, it's just a file system implementation on ECOS. So we have some examples. We will try to slowly open source them over time. Thank you.